about the vector triple product, and we have already discussed the scalar triple product and vector operations in our previous classes. You can go through my videos in YouTube and learn some of the facts uh, of vector algebra. And in the next class, as I promised during last class, we are going to discuss about the vector differentiation, and we are using the same book for now, as I found there are some stuffs that can be taught using this book. I am skipping some of the pages of this book, as they are not in the they're not very basics of mathematical physics, and since they have some other physical domain like mechanics involved, I don't want to introduce those things to you now. So I'm skipping this part. It shows how the vector differentiation works using the first principle, how the motion in a plane can be defined in terms of vector algebra, and how we derive accelerations and velocity of a particle moving on a plane. But for now I'm skipping it. We will be covering this chapter or this part of the vector algebra once we go to the advanced vector algebra kind of stuff. Currently we need to learn the basics first, and then there are some theorems that we need to learn. So I'll directly go to one operator that is most versatile in mathematical physics. It's called the del operator or the nabla operator. You can see the operator here. It's a vector quantity, and I'll show you how you can write this vector and how it works and what does it mean in mathematical physics. And it is denoted as the inverted triangle, and remember it's a vector quantity, it's not a scalar quantity. So this is expanded as, you guys might be aware of differentiation and partial differential stuffs. If some of you are having trouble in understanding partial differential equations or differentiation itself, please post your doubts in the comment section, and I'll probably cover a class on that. For this class, I am assuming that you do have idea on vector differentiation. So I'm just going directly to this del operator. It's written as I cap del by del x. This is small del, that one is big del, like small alphabet and big capital alphabet in English. So I cap del by del x, that means you will be partially differentiating the x component or the component towards the x-axis of the vector or scalar quantity. I'll just introduce those things soon. Plus j cap is the unit vector towards y-axis, and that is why you are partially differentiating the stuff with del y. And then the third quantity is k cap, and you write del by del z or g. So this is the expanded form of the del operator. You see I cap, j cap and k cap are there, so the resulting term will be a scalar quantity or a vector quantity depending on how you are using the del operator. If del operator is involved in a scalar product, as we learned in our previous classes, the output will be a scalar quantity. If it is involved in a vector product, the output will be a vector quantity. And each of its operating any vector or scalar quantity with del operator has its physical significance, and Because of its physical significance, we do use this del operator a lot. So I'll quickly go through the book first, and then if something is there that I feel that I need to explain, I'll use this textbook. So remember, this book is putting E cap, E2 cap, and E3 cap as I cap, J cap, and K cap. But the most versatile used term is I cap, J cap, and K cap for unit vectors towards X, Y, and G direction. So it says that a del operator can be expanded as this, and if you are trying to multiply this del operator with a scalar quantity, here the scalar quantity is phi. So going back to our notebook, if you write that you want to multiply or operate this del operator with a quantity called phi, and phi is a scalar quantity, mind it. So this kind of term is known as gradient. We call it grad or gradient when there is not a dot product nor a cross product. Means del operator is operated with a scalar quantity. Had it been a vector quantity, you have to use a dot product or a cross product. Since it's a scalar quantity, it will simply multiply. Means you can expand it like this: del phi by del x, del phi by del y, and del phi by del z, and you can erase this. So basically, when you are using the del operator on a scalar quantity, the scalar quantity becomes a vector quantity because it has, you see, it has a I cap, J cap, and K cap attached to it. So if the scalar quantity is say 5 or anything, then because of the multiplication of I cap, J cap, and K cap, it will become a vector quantity. So let us say how you will be doing it. Let us say phi is 2x. So this will give you an idea of how partial differential operator works. Plus 5g or g square. Okay. So this is a scalar quantity because it doesn't have I cap, J cap, or K cap. So it's just a scalar quantity. It doesn't change its direction, and it's a stagnant number. For a certain number, some certain value of x and g, the value will be constant, the value of phi. So when you apply del operator here with phi, what will happen? So how you operate partial differential equation? You have to see what term is there at the denominator of the equation. For example, here x is there, here y is there, and here g is there. So for this operation, all the components which doesn't have uh, I can write it g for easier understanding. I'll show you how higher power are used in the later class. So when you are operating del by del x, all the component that doesn't have x will vanish. So what you will be doing here is you will be writing I cap del 2x by its 2 del x plus there is no component of y here, so everything is 0, plus k cap. I'll erase this so it will be easier to understand. K cap and there is a component of z called 5g. So del 5g by del z. So this is what it will look like. Means when you do the partial differential equation, you know del x by del x is 1, so it will be 2 I cap plus 5k cap. There is no component for j cap because there was no term called y. So there was a scalar quantity phi, and you did a operation called del operation or gradient operation, and you reach to a point where you arrive to a vector quantity. It's easy to understand. Means if you are multiplying a scalar quantity with del operator, you'll get a vector quantity. But what does it mean? Why we'll use the del operator? As you can see, it differentiates. It uses the differentiation. So it has some application that is quite similar to the application of derivatives and integrations. Let's see what's that. So we understand gradient of phi, we write it like del phi or grad phi, and it's always a vector quantity. You'll arrive at a vector quantity. So we'll see how it works in see, this book has just reverted the stuffs. You know the del operator at page number 37, but you know what is gradient at page number 35. So that is why people get confused. They don't know what is being done. So before we go to the vector differentiation, that is called the gradient. Vector differentiation means you are differentiating a scalar quantity with del operator, which is a vector quantity. So that is why it is called vector differentiation of scalar field, because phi is originally a scalar quantity and del is originally a vector differentiation quantity. So what it says, given a scalar field which is phi x1, x2 and x3 or xyg, it's always easy to write xyg, which is differentiable at all point. Differentiation is something that you need to have a basic idea to understand mathematical physics. I strongly believe that you must have done your basic mathematics classes, and if you have done it and you have some doubt or you have not ignored it or whatever is there, you can write to me and I can take 1 or 2 classes on basic integration and derivative, and probably that will help. I will not go through the mathematical formula or formulation of derivative and integration, but I can take the classes of applied use of derivative and integration. Please do comment your views on that, and based on that I'll take a class. So now you know that phi is written as x, y, z, and let us say a changed unit term means infinitesimal, means very small change in phi is written as d of r. R is a bold quantity because this change will have a direction. It cannot be without a direction. So it will be like dx, dy and dg, the three axes. So now if you want to do the differentiation of phi, you'll write it like this, which is known as Euler's theorem. Because phi is a function of x, y and g, you'll have to write partial differential equation of phi by del x. Since del x is there, you'll have to multiply it with dx. And same way, partial differential equation of phi. So I'll write it down for easy understanding. So d phi can be written as, remember what is d and what is, it's a weird symbol, d phi. D phi is derivative of phi, not the partial differential equation. So there is a theorem called Euler's theorem that says that if you are doing a full derivative of a function for which you don't know the terms like this, if you want to write it in generalized form, you'll write partial differential equation of phi with respect to x. This is dx, remember. This is not del, this is d. So it's a full differential of x. Similarly, partial differential equation of phi by del y dy plus partial differential equation of phi by del z dg. Sorry, dg. So you have to write it, the derivative of x like this. But here you can divide this quantity in two terms. If you just remember our scalar product of two numbers, how does it work? You just omit, you just multiply I cap with I cap, J cap with J cap, and K cap with K cap in scalar product. So if you see, there are, if you imagine there are two components, and I'll change the ink, this one and this one, and this one and this one, and this one and this one. So if there are two different coefficients multiplied together, you can always write I cap del phi by del x dot I cap dx, and so on. So with that, you will know that what you are writing is I cap del by del x plus j cap del by del y plus k cap del by del g into phi. This is a vector quantity now, and you're multiplying with I cap dx plus j cap dy plus k cap dg. So you are multiplying two vector quantities in a scalar product to get this scalar quantity. So that is what it means. And as you remember, this quantity is the del operator. So you are making a gradient of a scalar quantity, and it is multiplying, if you are multiplying it with a small change in that direction. So let's see what does it mean. As you can see here, Delphi dot dr. Dr is the small change in the phi function, and you're arriving to a point where the derivative of phi, or the vector differentiation of phi, is equal to del phi dot dr. Now you see this is a scalar quantity, and the product will be maximum when cos theta term is 1. For a cos theta to become 1, you need to make these two vectors parallel. Minus phi. So what it does, let's see. It says the geometric interpretation of Delphi can be written like this. See, there are two vectors r and slight change in r. That is what we were seeing, r plus dr. So r vector is from 0 to p, means the origin to p, and r plus dr is from origin to q. So the vector from p to q is the infinitesimal change in r, that is dr. As of here, and this surface is the surface or the scalar function phi. I'll take a pencil here. This surface is phi. So you know on a function phi, this is a phi function. We are changing a quantity from this point to this point, and the change is known as dr. Okay, so when you are taking differentiation of this function d of phi, you'll arrive to a point which is equal to del phi dot dr. When del phi and dr are at 90 degree to each other, you'll get the derivative to be 0, and if cos theta term is 1, for that the small change has to be done in parallel to this. This is how the first vector differentiation of scalar product works, and we'll go to the second part where we are doing the vector differentiation of vector field, which is again two parts, dot and cross. We'll discuss those things in our next class. For now, I feel it's pretty much to digest mathematical physics, because there are a lot of new stuffs at the beginning which you do not learn during your uh, school days, but we have covered pretty much of the basics, and now we'll go to the vector differentiation of vector field, and then we have another thing to learn. These are now the derivatives, so means the other operators like Laplacian and all, but gradually you'll be used to these things, and there are not many new stuffs now. After the del operator is read, we need to learn one more stuff called the curvilinear coordinate system, which will tell us. So far we were learning the coordinate system in xyz plane, but what if we have a spherical coordinate system or a cylindrical coordinate system or a coordinate system with n dimensions? Yeah, it's not practical that you'll have more than 3 dimensions in a coordinate system, but for simplicity of a generalization of our stuffs, we read a stuff called n-dimensional coordinate system, a coordinate system that is imaginary and it has n number of dimensions or degrees of freedom. So we have two stuffs left before we can go on and learn the theorems, and once we have the basic idea of how the vector quantity works, what is scalar product, what is vector product, and what is the del operator doing there, and if you have a clear idea of all these things, probably mathematical physics will not be very tough. And with this I'll give you some of the formulae or some of the shortcuts to remember. some of the easy to go formula for uh, vector triple product, scalar triple product, how associativity works, and all. And then we'll see the coordinate system, different coordinate system, and that's pretty much it. Once we have the coordinate system knowledge with us, and once we have vector algebra knowledge with us, probably mathematical physics will not be very tough. So see you in our next class, and I hope you understood what we read today, the gradient and the del operator. If you have some doubt, you please mention it in the YouTube link, and I'll probably answer it within few hours of your post. Thank you very much. Bye. Have a good night.